XP Solutions XP Live webinar. My name is Jessica Jeffries and I am the Products Manager here at XP Solutions. Today's webinar, Hydraulics 101, is a follow-on from our popular Hydrology 101 webinar earlier this year. You'll find all our webinars recorded and available online, so if you missed a previous webinar, you can easily catch up. I'd like to first introduce our presenter for today. Gavin Fields is a Senior Water Resources Engineer at XP Solutions with over 10 years of engineering experience working on a wide range of stormwater and flood modelling projects using XP products. In the Hydraulics 101 webinar, Gavin will introduce the theory that you'll need relevant to building and reviewing stormwater models. He'll go through the effect of structures on the hydraulics and talk a little bit about how to build those models in the software. XP Solutions is a company that produces software for modelling wastewater, stormwater and floods. Most of you will be familiar with some of our products, the main ones you can see on the screen there. We focus on building high-quality graphical user interfaces that work with our analytical engines to allow you to import, build, run models and also review the results. The equations used in the software will be described in more detail today by Gavin.
Welcome to today's webinar on Hydraulics 101. We'll try and keep today's session at a reasonable high level. We don't need to drill down into all of the theory in a brief webinar, but hopefully everyone will get some good bit of an update on hydraulics as a reference. So up front, hydraulics is fundamentally the assessment of fluid flows. In the stormwater world, obviously the principal fluid of interest is water, and so for today's purposes we will only be talking about water and not oils or other compressible fluids. They do sometimes obviously display characteristics that are slightly different to that of water. Where does water come from? From a stormwater perspective, obviously, the hydrologic cycle feeds us with our inflows to hydraulic assessments. And like Jess made comment earlier, I do refer everyone back to our Hydrology 101 webinar, which again is available on our website if you did miss that presentation previously. So the aim of hydraulics is to basically assess, define how water flows, derive magnitudes, i.e. peak flow rates, volumes, and the general dynamics of flow as it moves through either a pipe or an open channel or other specific structure. Obviously water typically flows downhill, but sometimes it doesn't, and in those situations when it doesn't flow downhill, when it's flowing uphill, its energy is basically derived from an external source. And so on this central image, this is a photo from the tsunami in Japan a couple of years ago, and obviously there was some seismic influence that added energy to the ocean, and that energy was translated into the water body, obviously the Pacific Ocean, until it breached the physical structure that was the mainland. Other sources of energy are actually the sun and the moon, and this is a novel photograph of mine where you're actually looking at the sun and the black part is actually the moon overlying the sun. So the moon obviously supplies energy to the planet, and that is the basis of our tidal influences, which also affect boundary conditions hydraulically in any calculation set. The last place that water may obtain energy from is mechanical sources, of course, and I'll talk a little bit about pumps later on. The general theory for hydraulics is derived basically from the great work from Newton. So Newton's second law of motion, which is force equals mass times acceleration, is the fundamental law that drives all hydraulic assessment. From Newton's second law, the principal equation that most stormwater engineers and hydraulic engineers would be familiar with is the continuity equation. So the continuity equation allows us to maintain the mass component from Newton's law of motion, where volume and flow are a function of area. And obviously make that comment that continuity does maintain mass and therefore volume. The next part of Newton's law relates to acceleration, and therefore momentum equations start to help us define flow and directionality. There are numerous equations for momentum, the dominant of which is the dynamic wave equation. And that's an equation that was derived a couple of hundred years ago during the 1800s, and other equations that are very familiar to stormwater engineers, such as the kinematic wave, Chessy's equation, and the Manning's equations, were all fundamentally derived from the dynamic wave equation in the ongoing development of hydraulic calculations. The St. Venant equations are another strategic equation which allows us to understand the flow of fluids under pressurized situations. And interestingly, although the Australian rainfall and runoff documentation, which talks about the St. Venant equations, states that computers weren't able to satisfactorily calculate that particular equation in the late 1980s. Obviously computers have improved since then, but the raw equation was actually derived in 1871, so it took a while for computers to catch up to the hydraulics of the late 1800s. From these equations, obviously, we've developed models over time, and there are two functional types of models to assess hydraulics. We have steady-state models, which rely on approximation methods or simplifications of the dynamic wave equation. Manning's equation is one of those, of course. I made that comment before, as well as the kinematic wave equation. And for those of you who aren't familiar with the kinematic wave equation, the pure simplification there is that the energy grade, which I'll talk about in a moment, is equivalent to the slope, or the bed slope, and that's the fundamental simplification of that equation. Or alternatively, fully dynamic models, such as a couple of XP's products, which include XP Storm and XP Swim, allow for gradually varied and unsteady flow in any given location. And dynamic models also allow for variable inflows and variable boundary conditions. And those boundary conditions, when we think back to those photos before, if we had tidal influences from the moon, they're a discrete boundary condition that does change rapidly with time. This is a nice overview that we've obtained from a standard text which describes some of the differences between pipe flow and open channel flows for stormwater applications. And I won't go through this in any great detail, but hopefully that's something that most of us will be generally familiar with, and this provides a nice bit of an update on some early learnings if you've been in this space for a while. The next part of hydraulics is to assess structures, of course. Engineers and designers live in the world of structures, whether they be natural structures, which would be deviations in terrain and physical changes to the landform, or constructed elements such as pipe networks, which have manholes, pits, access chambers, etc., and how each of these elements will fundamentally affect the hydraulic characteristics of water. When controlled situations, we develop physical structures such as weirs, and we've got some a nice slideshow video that we'll present in a moment on the performance of flow through weirs. And this fourth photo is an interesting one, where this is actually intended to be an orifice plate, and this is definitely the odd photo in this set where the orifice plate is actually not restricting flow as it was intended to do. So this is a bit of a failure in construction, and unfortunately these are things that engineers do need to be careful of pursuant to their calculations. Last slide photo there is of a a concrete flapgate arrangement, so a control structure, and this is actually trying to limit saline influence on a what is a brackish lake across the other side of the road. Weirs are a really important hydraulic structure that assist engineers in doing a couple of activities, the primary of which is to store water on the upstream face. So they're very useful for detention basins, ponds, lakes, dams, etc. And then secondarily, they assist us in minimising energy and achieving minimum energy conditions, particularly in a broad crested environment. And so we can see in B in particular, which is a broad crested bottom sill weir, which is actually affected by a downstream condition, but we do start to approach minimum energy conditions over that structure. And by all means, there is lots we could talk about on Weirs, but for the scope of today, we'll try and keep things reasonably fast-paced. This is just a nice little video that hopefully this does display well at your end, showing the performance of a weir in a hydraulic laboratory where flow is fed onto the weir, and we can see that sharp decline in water elevation across the weir structure itself. We see the plume of water on the downstream side, and on this initial condition we have a zone of aerated water. Oh, I'm sorry, something might have... Yep. Hydraulic models, we usually assess this kind of behaviour in separate ways. The XP products at a technical level typically aren't able to provide some of the detailed hydraulics that we might have seen just at the end there with the waveform. And if you're interested in waveform around particular structures, you would need to consider computational fluid dynamics, which is definitely an advanced component of stormwater assessment. Now, Weirs obviously as being a regular item, other physical controls do sometimes take the form of proprietary products. And in this quick animation, we have a what is called a hydrobrake, which is a flow control device, a proprietary device that acts like an orifice in that it does throttle flows, but as flows increase on the upstream side of this particular proprietary device, it changes the behaviour of flow through itself into the downstream pipe network or open channel in a way that it induces a vortex. And this is a very specific hydraulic activity, and there's a lot of detailed hydraulics that occur to create these very turbulent regimes. But again, it's very important that if we were to have access to these kind of products, that we're able to model them in a suitable way. Other key aspects that affect hydraulics of flows typically come back to those energy equations and the momentum equations, and where we would definitely be interested in understanding losses associated with physical impacts, so the physical structures, be they channels, inlets, outlets, etc. Another important component of the energy equations does relate to the effect of friction. Hopefully most people would be familiar with Manning's roughness coefficient, the N value. And the next slide shows some examples of various Manning's values for different surfaces. So in an overgrown channel, Manning's values can increase as high as 0.15, very high for very rough obstructed flows with debris, etc., to well-maintained grass channels, concrete pipes, plastic and even glass or smoother systems. And one quick note is, of course, that as the Manning's roughness value increases, that does affect the performance of the conveyance of any element, and typically the depth of flow will increase as the resistance itself is increased. And that change of water elevation is a key aspect that engineers need to assess And the key outcomes here are to determine the hydraulic grade lines. The energy grade line, the red line at the top, is a function of the velocity head. So it's the velocity squared divided by 2 times gravity. And that's the separation between the hydraulic grade line and the energy line. The hydraulic grade line, of course, tells us water elevations, and that can assist us in designing infrastructure for upgrades. And so that leads us to the practical applications of hydraulics. Engineers will often be interested in assessing existing conditions for hydraulic situations, and be they river systems, existing pipe infrastructure, if we have some legacy infrastructure in play, or a variety of other elements, sometimes with the pure intent of improving those conditions to protect infrastructure, or make planning decisions for upgrades or development. And if we're going into the upgrade or development sphere, then we would then be very interested in understanding how to size infrastructure in the form of pipes and those other key aspects. When we think back to the hydrologic cycle and the impacts of change on hydrology, we will often try and maintain existing conditions in terms of peak flow rates as more commonly, and in some instances we may even be interested in maintaining the same volumes of discharge coming off a site, and therefore detention and retention systems can play a very important role in a hydraulic assessment. I just have another quick video of an existing piece of infrastructure that has failed. Hopefully this will come up. And so in this particular situation we have a minor drainage system that has surcharged onto a roadway and caused even some parked cars to float. I might see if I can replay that just to show that again. And we can see that we have a clear point of surcharge from a manhole in the middle of this road, and from an assessment perspective it would be very important to be able to model this and determine the location of that kind of failure from a modelling perspective, and that could be then used to plan for emergency purposes and either road upgrades or additional pipe upgrades. When it comes to sizing infrastructure, obviously culverts and pipes are number one on the list of items to modify, whereas we can also improve channels, add smoother surfaces, change that roughness coefficient hydraulically, and improve the rate at which the flow crosses any given location to try and get it to its ultimate outlet. An option that is rarely used, I suppose, in a stormwater sense, except in very specific applications, are pump systems. Obviously most engineers would be familiar with pump systems in a sanitary or sewer environment, but there are many instances where dewatering applications require pump systems to again apply additional energy to that water body or column, and one of the important elements in designing those kind of systems is understanding how the downstream infrastructure resists the performance of that pump, particularly as velocity does increase in an enclosed environment. We do expose ourselves to increased head losses or energy losses due to those roughness effects. And one note that a number of simplified modelling packages generally don't include that kind of functionality inside their standard suite of characteristics. And the last major piece of infrastructure to size, and on a regular item, even on small allotments that are subject to development, is detention and retention systems. And so this particular photo shows a pond system that actually does have an internal weir, and we can see the constriction that is applied along a subsurface sub-water bund, as we can see the vegetation becoming proud of the water body at that location. The behaviour of this pond is to protect partially the township that is down below it from the upstream catchment. Once we've got a general understanding of the hydraulics of any given site, the next step is to work out how to build a model to derive information in the form of results to make those informed decisions moving forward. There are typically three general types of models, hydraulic models: 1D node link-based models, more recently 2D surface models, and in conjunction with that, combined 1D, 2D models, which are often referred to as those integrated 1D, 2D models. For 1D node link structure models, nodes typically represent junctions, manholes, inlets. They can often model catchment areas, be the point of the hydrologic connections into the software or into the model, outlet structures, and major storages, which could be in the form of that pond like we saw on the slide 2 ago. Building up into a network, once you've defined your node locations for the various elements, we then link these with either bridges in a river environment for trafficability purposes, pipe systems, channels, and of course pumps, and then some of the more specific items like orifices, weirs, rating curves, or proprietary devices if they form a combination of those elements. Hydraulic packages always require data. Data is always king for modelling purposes, and on nodes the key pieces of information do relate to the storage characteristics of that point, whether it be a standard manhole or a detention basin. It could be a 10 hectare element represented by a single node. The geometric characteristics of a node typically relate to information based on terrain, and they would include invert elevations, and for pipe systems that invert could be below the ground, and then you would also need to understand the surface information for surcharge purposes from the video a couple ago. And then finally, hydraulically, understanding how the flow gets into or out of the system always typically happens on a node. Link data requirements relate to, again, geometry, and in this instance, by joining two nodal elements, we would need to understand the upstream and downstream invert elevations, and again, details that relate to the ground. So in a riverine system or a creek, we would want to understand bank situations to determine whether or not flows move into a floodplain or over a side weir or any other structure. Could be a levee. And with that, from that geometry, again going back to the continuity equation, based on its cross-sectional area and inflow, we can then assess velocity, and that is done in conjunction with components of the energy equations, with roughness and structure impacts. And I make note that as part of the preparation for this webinar, we did actually receive a couple of queries from some users, and I'm going to answer those at the end of this particular webinar on some very specific items to do with inlet structures. So hold tight, we'll talk a bit more about those at the end. But quickly on inlets and outlets. Inlets do come in various forms, and so this particular inlet serves two purposes. It's an overflow relief from a water body, but it also acts as a surcharge relief, as this is actually connected to a tidal exchange system to keep the lake itself in an actually fully saline environment. And so pretty specific piece of infrastructure. Field inlets or gullies are the next most common type of inlet, apart from head walls, and that particular photo in the middle does provide a couple of opportunities, and it's located in what is a temporary cover on a bioretention or a water quality device. where the extended detention is being controlled by a combination of effects which include a low flow weir, the main weir at the lip of the pit, and then finally for high flow situations the grate at the top. And the grate's there for public safety purposes, of course. Head walls can form both inlets and outlets, and in that particular slide, this particular head wall is an outlet from a gully pit that is located in the curb on the street adjacent. Once we build these networks together, we then are very interested in understanding the influence of the hydraulics on this particular system. And we can see here that I've just shown very quickly a storm. I'll see if I can replay that again just to get that to happen again. Yep. So as the storm rises, we have significant overflow at two locations, and fortunately in this particular applications they were detention basin points. They were forced storages into the model, and the magenta line represents the maximum hydraulic gradient line from this particular model. And then we move into 2D models, and so from a 2D model perspective we need to understand the surface terrain, which has been triangulated on the image to the left. Many 2D models then regularize that into a grid format to then take the hydrologic information in conjunction with land use details. And these land use polygons we can see on the right hand side tell us about not only roughness characteristics but also infiltration characteristics. Could be geologic details which do relate to infiltration. And once we've paired that series of information together in a broad sense, we can then start to derive integrated 1D, 2D models where we can pair both data sets together. And as an output, we would expect to see inundation plots which tell us information about depths across development area, as this is a particular example. This particular example wasn't interested in the dynamics of the creek system that surrounded this particular area. However, this model could be extended, of course, to take that information hydraulically into account, although boundary conditions were considered. Other information that you can obtain from hydraulic information you can derive from a 1D, 2D model does relate to both velocity and elevation, and that can produce hazard information and help us prepare to understand, in the event of a major event, what is the risk of any particular area in this development in being able to leave under an extreme or extreme weather event or storm event. So that brings us towards the end of today's session. We only wanted to have a relatively brief session today. So the first question that came in through the during the week as we were preparing for this particular webinar related to the inlets of highway culverts. There is a very specific document that I'd like to refer everyone to, which is the hydraulic design of highway culverts. It's from the United States, and it provides a series of nomographs which talk about how inlets, head walls, embankments affect the flow of water into hydraulic structures. And the question was specific to our software, and whilst we didn't go into our software too much for today's webinar, we did want to highlight on this particular one. But on links within the software, under the conduit factors area, we have a couple of key items to point at for this particular topic. The first of which is the inlet type, which sits in the middle of this pane, and also the entrance and exit losses. I've actually had this from a number of users over since my time with XP began a while back, and do these two parameters talk to each other, or are they one and the same, has been the general question. And I can confirm that these impacts are mutually exclusive in the calculations, and that the entrance and exit losses themselves relate to the characteristics at or within the pipe itself in response to issues with the vena contracta as flow enters into the pipe, whereas the inlet type itself and these nomographs provides information based on the upstream and downstream components of the inlet, and that helps the software assess and define whether or not that particular culvert operates under inlet control or outlet control. And that's a very specific area for pipe or culvert hydraulics, but I can confirm that definitely you would need to include the inlet type as well as an entrance loss, in my opinion, to suitably model a culvert under that arrangement. Another question that came in during the week related to tailwater effects. And again, inside the software, tailwater effects and boundaries can actually be put into the software in both 1D and in 2D. But for 1D purposes in the short term, the software has a number of options that can apply to pipe and open channel situations. And in an ideal world, we would all love to be able to get to this type 1, the free outfall scenario. And whilst it would be great to say that we could all model to a waterfall where discharge does act without any downstream constraint, that's typically not the case. And so free outfalls or fixed backwater outfalls do need to be located strategically to ensure that they're located away from the area or point of interest that you're modelling. Other models give very specific suggestions. However, I believe that as engineers we always need to make good judgment when you're making an assessment, and I would not, for example, expect to see a free outfall on a pipe system, because a free outfall on a pipe network would provide potentially too great a relief at that location in the model, and I would try and push or build into my hydraulic model some additional overland flow away from the pipe network itself to allow space for any influence that the outfall has on the pipe system to occur within the open channel itself, rather than potentially affecting the pipe system, because it may be that you could falsely undersize a pipe or a culvert in that kind of an arrangement. Obviously, we see in the middle here we have a number of tidal control options, and those tidal control options can be used in conjunction with sinusoidal coefficients that you would need to obtain from your local maritime organisations, or do some physical measurement yourself, or find a tide chart or other piece of information. And then the final three options that we have in the software relate to flow history details, and that's very useful if we had a gauged catchment. Rating curves similarly, typically based on observation. And the last option, which is this type 6 option, is again probably the preferred method to use rather than a free outfall or fixed backwater if you weren't able to successfully extract a natural section for any great distance downstream of a pipe system. A type 6 outfall may be appropriate in that pipe network situation. And of course you can contact us here at XP Solutions on the relevant points of contact in your area, and my direct email there is gavin.fields@xpsolutions if you do have any technical queries aimed at me.